Yesterday, we talked about how to determine if two functions were inverses of each other. And we do that by putting them together in a composition. We have to do it both ways. If the composition simplifies to just be x, so if like f of g of x simplifies to be x and g of f of x simplifies to be x, then we know that we have two inverse functions. So what we didn't go over yesterday was how to start with a function and then come up with its inverse. And so the steps that I have here on the screen, these are the ones that we're going to be following to algebraically create or to solve for the inverse of a given function. 5 steps, some of them are much shorter and faster than others. So first thing, we always want to test to make sure that there will be an inverse function. So a quick horizontal line test. We don't necessarily have to do the horizontal line test. Like if we already know that it's going to be a parabola, we can say, yep, that's not going to work because that's a parabola, it won't pass the horizontal line test. But it won't be too difficult just to like type it in Desmos or something and get a quick look at the graph. Just make sure we do have an inverse. Second thing, we're going to write it instead of regular function notation, like f of x equals and then a function rule. We're going to replace f of x with y. That's just so that it's simpler to do this process. Then we switch the x and y variable. So where the x was, we put a y, and where the y was, we put an x. Then we have to solve that new equation for y. That can be pretty tricky depending on the equation. If it's a really simple equation, then it'll be pretty simple to solve for it. If the function is more complicated, then solving for it could be fairly complicated. Just kind of depends on what we're working with. And then once we get that new equation solved, we write it back in function notation using the inverse symbol, f inverse of x. I went through that pretty quickly. It'll make a lot more sense as we actually just like sit down and do one. And we'll start off with an easy example. So first of all, we got this function right here, and we could go ahead and do the Desmos graphing if we want to, but I already know that this is just the graph of a line. So this is just going to create a straight line with some slope to it, but it's going to create a line, which I know will pass the horizontal line test. So I'm not going to do that first step. What instead I'm going to do is just jump straight into actually solving for the inverse. So what we do here is, first thing I'm going to do is instead of writing f of x, I'm going to write it as y. The next step, I don't remember the numbers right this second. The next step is going to be to interchange or switch the x and y variables. So where there was a y, I'm going to put an x. And where there was an x, I'm going to be putting a y. And now sort of what this signifies is I'm switching the input and the output variable. And if we sort of remember how inverse functions work, that the input for one function becomes the output for the other function, and the output for the other function becomes the input for the other one, and it's kind of because they undo each other, right? We talked about how one function mapped a 2 to a 6, and the other one took that 6 and mapped it to a 2, right? So the input for one was the output for the other, and the output for one was the input for the other, and it kind of has this relationship. So when we switch the input and output variables, we actually create a way for us to have an inverse function. And now it just becomes a matter of solving this new equation for y, and that's going to create our inverse function. We're still going to have, it's not going to be like y equals 7. We're going to get y equals and then a function of x. So I'm going to give myself some space to do this because this is the longer and more complicated process. So keeping in mind I'm solving for y, I need to get rid of everything over here that's not the y. So I just multiply both sides by 2. So I get 2x equals 5 minus 3y. Then I need to subtract 5 from both sides, get rid of that. So I end up with 2x minus 5 equals negative 3y. And then I'm going to divide by negative 3. Since this negative 3 doesn't divide nicely, I'm just going to go ahead and leave this as a big fraction. And I've kind of created my inverse function. There's kind of one little thing here that some people get really nitpicky about. They don't like to have negatives in the denominator, so they would prefer to apply that negative to the numerator, but I don't really care. I'm just going to leave it like this for now. So this is kind of my inverse function. So now I'm going to write it in function notation. So f inverse of x is equal to 2x minus 5 divided by negative 3. And so that is our inverse function. It's not too complicated. A lot of the steps are pretty simple, just in terms of switching x and y, writing it with a y instead of f of x, and then going back to function notation. All that stuff's pretty simple. This process of solving can be complicated if our equation is complicated. Just depends. But that's our inverse. When you look at the two functions, you should sort of notice their differences, how one of them has I have a positive 5 in this one, right? And over here, I have a negative 5 in this one. I'm dividing by 2 in this function, where I'm multiplying by 2 in this function. In this one, I'm multiplying by negative 3, but in this one, I'm dividing by negative 3. It has opposites all over the place. Actually, every operation is sort of done in the opposite way in the other function. So that kind of gives me a hint that they are inverses, along with the fact that I created it to be the inverse. So these two functions are inverses of one another. I'll clear this off in a second, and we'll look at another one. Okay, I'm clearing, and let's do a little more complicated one. Here we go. It's not too bad, but a little bit more complicated. So first thing I'm going to do is write it in terms of y instead of the f of x, instead of the function notation. So y equals 2x to the third minus 1. Then I'm gonna, the very first thing I should do is look at this graph and say, is this function one-to-one? Do the horizontal line test on it, make sure it works. I'm just gonna assume that it is. It would create this cubic graph that would look like this. I know that it's gonna be one-to-one, but we should look at the graph. I'm just not gonna do it right now because I do know that it would work out. Okay, next step, I believe this is step 3. Step 1 is check that it's one-to-one. Step 2, write it in terms of y. Step 3, interchange the x and y variables. Step 4, solve for y. Again, this is the more complicated step, takes more to do that, but this one not too bad. I'm going to need to add 1 on both sides. I get x plus 1 equals 2y to the third. I need to divide by 2. And I'm going to kind of move things over here. X plus 1 over 2 equals y cubed. And then last step, to get y all by itself here, I'll have to take the cube root. And I'm going to leave my function just like that. So it's going to be the cube root of x plus 1 over 2 equals y. That's not really in function notation, so I guess my last step is, instead of writing this with a y, is to go ahead and change it back to function notation and call it the inverse. Oops. It's not f. It's g. G inverse of x is equal to the cube root x plus 1 over 2. So that's our inverse function. Again, as you're looking at it and comparing it to the other one, you should see the opposite things going on. Instead of a minus 1, I have a plus 1. Instead of cubing, I have cube root. Instead of multiplying by 2, I'm dividing by 2. It's got all these opposite things going on. Just has to happen in the right order, which is why we had to solve for it. We solve for it just so that we make sure things are happening in the right order in our equation. Not too bad, though. Let's go ahead and move on. We have 5 minutes, so. All right, I'm gonna do this one pretty quick. Same idea, just finding the inverse of this function. So I'm gonna, again, just gonna assume we're good to go in terms of creating that this function's one-to-one. It's a good job. It's a square root graph, so it's gonna look something like that. So I know it's one-to-one, so there should be an inverse for this. It's just a matter of solving for it. There is a bit of an issue with this once I solve for it though, so I'll get into that in a second. So write it in terms of y, switch x and y, solve for y. So I need to square it to get rid of that, square both sides. So I get x squared equals 2y minus 3. I'm going to go ahead and add 3. So I get x squared plus 3 equals 2y. And I'm going to divide by 2. So that I get x squared plus 3 all divided by 2 equals y. So that's my inverse function. Bit of a problem with this. This looks like a quadratic, right? This one here is a quadratic, so this is going to make a parabola. So even though this function was one-to-one, the inverse was not one-to-one when I solved for it. So this function right here all by itself is not a proper inverse. Even though I technically was able to solve it and there should be an inverse, what we have to do in cases like this is we say, fine, this is the inverse, but it only works for certain numbers. It doesn't work for the whole domain of this function. They aren't going to undo each other for everything. It only works for the numbers that this function would work with. So this, as long as I define my inverse function to say that I'm only going to count this as an inverse when the numbers work with this one, then it's okay. It's called restricting the domain, and it's something that we can do. We can say that x has some restrictions, and in this case, x would have to be greater than or equal to 0. That's all we really care about because, well, technically I have some other restrictions to that, but it doesn't matter. Something like this has to be greater than or equal to 0. For the most part, we're just going to be dealing with functions that just totally work in these cases where we don't have to restrict the domain, or I'm not going to be too picky. You just solve for the inverse. You don't have to come up with the restrictions that it would have to work on. All right, I'm going to go ahead and move on to the very last thing. The very last thing is talking about the graphs. So here we have two functions. The f of x is right there, that cubic function, x cubed plus 3, and then g of x is right here. These two functions are inverse functions. We could get into the algebra or show it that way, but what I really want you to see is that when you look at the graphs of two inverse functions, what they are is they're always going to be reflections across the line y equals x. That's why I have that graph on there. If you flip the graph over the line of y equals x, it's going to be the graph of its inverse. And if you look at any individual point on the graph, you'll notice that they have the same coordinates, but the x and y values have been switched. So for the red graph, we have this point here at -1, -3. There's going to be a corresponding point on the other graph that has the x and y coordinates switched, -3, -1. And you could find a bunch of examples, like this point right here would be 0, -2. So I know there's going to be a point at -2, 0, which there is. And that's true for all of them. And where the graphs intersect each other will have to fall on this line. So in this case, these graphs only intersect in one spot, right there on the line y equals x. It's kind of a quick way that you could just check to see if you think two functions are inverses. You could just quickly graph them using something like Desmos and be like, yeah, they look like reflections, so they probably are inverses. It's a really quick way to do that. It's 11:05. That kind of covers everything from this 1.5. If you're having trouble on the homework, please let me know. You can come to my office hours. I'll be there today at 1:30 and Friday at 1:30 to get any help. Yeah. You guys can go to your next class.